Okay, welcome to a video showing the HDL workflow that I am using for the development of LibreSOC. So, yesterday I happily talked to myself for an hour. Realised that after I'd completed and said thank you very much and I'll upload the video that I haven't pressed the record button. So well, this time we're actually doing that. So this is a 4K laptop with 64 gigabytes of RAM, which I found has been absolutely necessary. The 3840 by 2160 screen. I've taken about 20 years to develop this FEWM desktop arrangement, and in the bottom right hand corner you can see I've got 6x4 virtual screens. Alright, and the reason for that is that I can easily flip was to the right. This is to the right again of that, so I've got a different context, and rather than I know it can fit multiple things on screen at once and have different contexts. So this particular arrangement here is for Coriolis 2, which is the which is by LIP6.France FR. It's entirely Libre licensed, no NDAs, place and route system that is what's the term? Program or function language is parametric. You don't write in some really awkward ancient obscure language called TCL. You don't half edit with the GUI and half do it with whatever. Everything is a Python program, the whole lot. So you want to define a block that you want to place it in a particular place. You call you get an instance. You call a Python function which gets you instance. You call another Python function which places it where you want it to be put. You then call another function to say please route with to do the subset place and route within that thing. All right. Here the context is that we have we're developing the main core, which again is in Python, using the MeGen. Yes, it's very common for me to do jobs pipeline grep mul, for example. I don't edit a file then exit it. I do ctags -r in the top level source directory. vi colon tag and then issue to scoreboard, whatever thing, like that, using vi. So I keep the context in of what I'm editing so I can flip between the two. And yes, because it is a object-oriented design spread out across multiple files, I really need all 11 of these 80 by 65 xterms. Then here, for when I'm doing research, there are some things which I need to look up. So this particular window is a mismatch of different contexts because it's the file that I'm looking up with. Yeah, you get the idea. Thing. And then down we have the LiteX simulation is over here. So I've got I've got the sim version of LiteX, which does automatic compilation using Verilator, over there. The FPGA and the LibreSOC 180 nanometer chip compilation is here. When that's running on the FPGA, that's connected to the serial consoles there. That's a Versa ECP5. You can also get a ULX 3S, which is 85K lookup tables, 85K LUTs, Again, entirely Libre licensed tools. No NDAs, no proprietary stuff, source code fully available for everything. And no fees either. Sound stuff, yeah. So and we go over here and then go down. This is yosys show LS180. I think absolutely massive, but it's so big it actually can't actually properly see the things. But that's just part and parcel of what LiteX does. Is it just generates one massive auto-generated Verilog file from the from MeGen, not NumMeGen, MeGen. It does the job. It generates the peripherals, so we don't have to worry about it. So going to this bug, we need to do a dry run of the GDS2 files for sending it out to IMEC. Tape out deadline is December 2nd, or so December 3rd. So first thing, so what we did was, what we're doing is in this window, I apologize, I remembered where these things are, so having the laptop shut down is a real nuisance. So that runs the core. It's intended, there's 12 different pipelines in this thing, so it's fan out. The thing, this decoder things here is we have a separate decoder for each pipeline. You actually pass the instruction along with the partially decoded for the operands that is needed. When it arrives at the front of the pipeline, goes through further decoding specifically for that, everything's associated with that pipeline, and it greatly reduces the fan out from the decoding of the power instruction set to the thing. Alright, so that created us a Verilog file. Copy it into temp directory, go here, go down. I've got a copy command there, copies into the LibreSOC directory. Now we can do make here. This make file will do the build, LiteX build for us with our LibreSOC 180 platform. Then from the resultant files, put it into use yosys to munge it and join the LiteX peripheral set to the core for us. Copy that into /temp. Copy /temp ls180.il non-generated full core. Right, I needed to update that. Right, now the reason for copying into /temp is because this is a chroot jail. This is this Coriolis 2 is running in chroot, which has a replicable build script to create it, so that we can do full replication of the GDS2 files, no matter where our things or a thing. It's not. I think that's critically important for things. People need to be able to generate exactly the same files without any of the software changing or interfering. So /build full. So I just issue a thing, just not another thing. This was something I was sorting out from yesterday. Changing over to a new I/O system, which is in progress. What I did there was there's a couple of signals that I had to add, which I'm now removing. Clean as. So back here in the this was the Litex peripheral generator, which needed to cut a couple of extra signals that weren't in the core itself, and everything. So I had to remove that. And over here, passing that over to Coriolis 2, there's an ilang file, always called RTL IL. RTL intermediate language. It's an internal thing for a yosys, which yosys then can convert to a subset of VHDL, which Alliance Coriolis 2 understands. And yeah, normally I put this into a no-hub file. You run it under no-hub, and I can have a look at it afterwards. I've already run it now. So basically, here's where we do the core development. I'll show you a little bit of that whilst this file that's running. So let's have a look at, for example, the multiply pipeline. It's declared as Python. Okay, there's no actual HDL in that at all. It's just declaration of classes using base classes. So you can see the here's the 3 stages of the pipeline. We get to pipe 1, 2, and 3. There's where the EQ statements to connect the stages together. Stage 1 is an input from a bit of pre-processing, mul stage 1 to text sign 32. So let's have a look at that one actually. 36. That's mul stage 2. There we go. There's mul stage 2. There's your actual multiply. That's combinatorial, and the output equals A times B. It's really quite basic. It's much more complicated as you go up the thing. One thing we do have, which I am shocked to find is not standard practice, industry standard practice, is every single unit, they're down to the leaf nodes, has a unit test. We do not wait until you get to the top level to create an overall systems integration test. In effect, we've got one, but it's backed up by the incremental things of each stage where we have reasonable amount of confidence in each level. So this is yosys doing the turning into net lists and BLIF files, etc., etc. So it goes Coriolis. So we go from the core, the main actual core, which is a power IC, open power instruction set core, which we called at the moment test issuer, because it's a test core and it issues instructions. That then has a couple of wishbone interfaces and things. I'll show you that. Simple as core. Nope. 5. Okay, here we go. So you've got the main core there. We'd have an instruction memory interface, which is wishbone. Self.imem. There we go. That's for the fetch units. A ZIX interface. That's XISES. That's equivalent to RISC-V platform PLIC, if you're familiar with that. The JTAG interface, well, we originally implemented DMI, debug memory interface, but then put a JTAG front end on it thanks to Staff Hagen's Chip for Makers code, which has an actual implementation of a tap test access point, JTAG tap point, full FSM. One thing when you're normally dealing with FPGAs, you get a bit of a problem in that the FPGA takes over the 4 pins, the JTAG pins, and you can't connect to it. You have to have a special shift. It's usually an undocumented interface where it does the shifting for you and throws you you think you have to shoehorn in. Whereas this, we actually want a full independent JTAG interface, and fortunately staff from Chips for Makers wrote one. So we're just using that. And then 20, and then now one other important aspect of this is that we LS180 pins, source spec 8%. I'm as a software engineer, I'm not the slightest bit interested in duplication of effort across things. So what I do is I write a function or a class which generates my pins into a machine readable format, and then throughout the rest of the code use that machine readable format and generate classes and functions which read that to give us the specifications of the pinouts. Because one of the things is that when you've got a JTAG tap interface, you can't you have to be able to mux the pins to into the JTAG interface and back out again, so that you can basically do a boundary scan on the pins. But I'm not going to do 128 pins or 256 pins where I've got the core has to have 128 pins, and then the JTAG has to have 128 pins, and then the actual IO ring has to have 128 pins, and you write the code by hand. That's insanity, and you're going to make mistakes. So do it all programmatically. So this is what this the specification is written as a Python program which outputs a JSON file. That is then read in here. So the pin dictionary gets passed in, and it creates these boundary scan lines things here, which are understood by the JTAG interface, and then also by a wishbone master to be able to directly access the memory bus even if the core's broken. I have no idea what that is. There's our DMI interface. So JTAG addresses IR codes 8, 9, and 10 will give us set address read and write read on the thing. And we decided also to add a couple of IO codes for completely shutting out the core, just in case the cell line goes belly up, and that would lock us out of the if the cell lines are from the bus masters on the core go belly up, then we're completely screwed. We can't access any of the peripherals over JTAG. So the idea is to be able on this test chip is to be able to shut as many things down and be able to do as much as we can. So that back damn doesn't have an SDRAM-DQ_I0net. I will have to sort that out. It was better than it was before because I messed something else up earlier. Sorry. We'll have a look at it in a minute. So again, here's the IO ring, and once again we read the JSON file. This is a bit of code munching for encoding psi of Coriolis 2 uses strings, whereas the standard JSON function passes Unicode. So I found this online, shoved it in here. Good piece of code. So again, here we read that SDRAM-DQ_I0net. That's printed out our JSON file, dictionary, the pin mappings, etc., etc. Now let's have a look. So what was it called? It was called SDRAM-DQ_I. Where is that? SDRAM-DQ_I. This is after the thing's been converted to VST to VHDL, a mini sort of thing of SDRAM-DQ_I_0 and no. What the hell? That is spectacularly weird. Explains why it's not working. So rather than that being a vector from 15 down to 0, it's gone and created a... Right, let's have a look. 16, that's 180.il. SDRAM DQI. What the heck is it connecting only to? Line 0, 13 to 0. Can you see that? That's connecting that to there, that to there. If they're all connected, it's the wrong one. Right, that'll be down in the LiteX code. DQ, nope. 5 SDRAM, DQ, SDRAM. Let's have a look at the 27. Let's have a look at the original Right, there's his SDRAM DQI. Here is our output. So this is quite thoroughly messed up. So this was auto-generated from MeGen by this code here. This is the LibreSOC 180 thing. So we declare the interfaces here. Here's the because okay. LiteX can only understand Verilog, so we have to output the core as Verilog. That's why we did that. This here, which then is imported as a foreign instance into MeGen, which we then have to declare in this I underscore thing and O underscore thing. That is a foreign import into MeGen, was what LiteX uses, but I parameterized it because, of course, you've got. If I show you the microwatt one, it's got that and that, and that and that, and that and that, and that and that and that and that. I think I just went, oh, for God's sake, just write a function to do it, because we've now got. There we go, make wishbone bus function. So rather than that, so that adds into the dictionary for the parameters there. Adds into those to the CPU, so you can actually connect up the CPU, and the MeGen code can understand the port that the CPU has, which is then connected up when you add the SDRAM. That bristles out an actual SDRAM, but you need to connect the wires up to the pads and then connect that SDRAM into wishbone interface to, so you get the idea. But also very inconvenient here, because we're doing the JTAG boundary SI, and the JTAG is in the core code. I route all the I/O into the core code, which contains the JTAG module, and then it routes back out again. It was a pain in the ass, but I did it. So SDRAM. So first thing we check is here. Wrong one again. If it's a SDRAM peripheral, go request. So this is, it's not as automated as I'd like it to be, but this is getting from our JSON file that declaration of the peripherals. I'd like all of this to be here, to be just part of LiteX, where we just pass LiteX the JSON file, and it auto generates the pin maps. We're not there yet. Make pad. Something strange going on here. SDRAM clock, SDRAM DQ, 14. SDR. Right. Immediate slice objects. SDR DQ0. So here type, it's an in try out. Get field from CPU of the I. Brackets index, so that's where our slice comes from. CPU pad, IO pad. Gets us a slice of the thing, but that's what's messing up. And I have no idea why. Very annoying. Wait. That looks okay. STRM DQI there, D1 there. Yeah, that looks alright, doesn't it? That looks fine. DQI. Right, what we're looking for is that goes to 0, 0, that goes to 1, 1, which it does. 2, 2, which it does. That's perfectly fine. You know what? Let's do that. Still fine. Still fine. Y width output 16, so this is having converted the .v file to ilang. It is readable. Not fine. Can you see there? The STRMDQI connected to STR DM1 core. That isn't fine. So it's yosys messing up. Damn it. Ah, right. 15 racks 1, so it's fine there. That's okay. Main DFI blah there. Yeah, that's okay. But STRMDQI STRDM1 underscore core I. Let's go back to the original Verilog, and carry on looking. There. And you see that TQM pad has been connected to bracket 0. Bracket 0, that's our problem. And that is which object is that we're connecting to? Test issuer. Test issuer. Right, and test issuer is the core, which is that. So it is goodness sake, it is this. I really don't like Magen. It's not obvious, and it has new Magen is written by an extraordinarily competent programmer, White Quark, who really knows what it's doing, and gives error messages at the time you're actually running the tool, whereas Magen its predecessor was a bit of a hack and hand outputs Verilog itself. And the idea is that you're supposed to use the Verilog tools to check that your code is correct, and of course it doesn't necessarily do that. And you now, rather than being able, because it's auto-generated output, it's almost unreadable to the point where verifying it is an absolute nuisance. So in this case, I think what it's doing is, because we're using a slice, as it's called, we're using an indexed bit, it's going, I can't be bothered to put it onto the slice, I'll just put it onto the signal. Of course it goes, it's 1 bit wide, and gives you bit 0 rather than the indexed thing that you actually wanted. Let's find out if that is actually true, or if it's my mistake. Try function, comma, pin, comma, idx. We'll soon find out if I'm babbling. Can you see that? I am telling lies. There we go. That is a 0. It's 0 constantly. Right. Okay. If function equals, then this is a really bad hack, but function is str. I really don't want to do this, but we've got to get it done. str psi Do we have any other information? Res pin function pin type. Damn it. I'm going to have to split the thing. Why is it going through to there? Because it's an individual pad. SDHSI, in pin splits underscore by underscore. We want the last one the output enable is different. There's only one output enable line per thing. Same for a batch of pins, but you have only one output enable. There we go. I think we're probably going to think, okay, all right, so 27. Yeah, there we go. STUMDQ 1414, 8, etc., etc. Brilliant. Okay, copy. Dots. Dots. Bill. Full. 31. Alright, so I can keep an eye on that. Okay, so to explain what we did there was... Yeah, we still play a recording, thank goodness for that. Messed that up last time. Right, so to explain what was going on there, I had messed up the indexing. The JSON file is supposed to encode this information for us about the numbering on the pins, numbering here. But it's actually encoded in a string. There's a number of others that I'm going to have to do as well. I have to do micro SD card as well, because that I know has a pad specification. 31. I'll show you those here. Okay, so I invented this system where plus on the pin name means it's an output. Star means it's bidirectional and minus obviously means it's input. There we go, there's an input there. So I squared S as master clock out, B clock, LR thing, data in and data out, DR minus and DR plus. So that information, so that function I2S, if you want, let's have a look, if you want a SDRAM, if you want a SDRAM interface, it returns you as bus pins and what's in, out, and what's the clock here, which then is used here to say that on the north side from pin 2 onwards, I want 30 pins, this next subsequent 30 pins to be dedicated to SDRAM. All right, and that will go onto the north side into the JSON file. Then Coreless LiteX will create the correct JTAG things. Saying communicate with the core. The core will create, also reads the same JSON file and matches those, and LiteX then passes it to Coreless 2. Coreless 2 picks up the exact same JSON file and generates the pins, but since I just showed up, messed it up slightly. You get the idea. No graphical interfaces involved in this at all. It's not quite true. Push T, make clean, make LVX. This is building one of the test programs. Make LVX, make view. Wow, a graphical interface. This is a new thing that Jean-Paul has done, which has allows multiple clocks, although we're going to use two. One is for JTAG, which is independent of the main system clock, but also allows multiple pads for ground and power for I/O and the main core. So we're going to have 3.3 volt I/O, VSS and VDD, and I think 6 or 8 1.8 volt core VSS and VDD, which, surprise, you can see these here. That's external, that's internal, so that's for the core. So E for external goes on the north side. There's 2 pins there, which will be those 2 there in the larger chip. Anyway, I mean, you get the idea. I'm going to leave it at that. Get the general idea, I'm sure, from this, and thank you very much, and thank you to Pepijn for this opportunity. Also, thank you very much to NLNet for sponsoring this project. I'm actually amazed and delighted that they funded this. Thank you.